So sometimes you want multiple 3D printed parts to stick together, and you don't want to use screws, you don't want to do magnets, you just want something to snap. Just snap, snap, snap. So in this video, we're going to go through 5 different ways about how to make items that will actually allow you to connect them together really reliably. And we'll show you how to design them so that they work on any machine, anytime, anywhere, and are never dependent on settings. Comment down below if there's any other that you would like us to see at the end of the video. So there are a lot of different ways of sticking 2 parts together. You can screw them together, you can glue them together, or you can design in fasteners themselves into the parts so that they snap together. But in this video, we're going to go through some basic connectors to join larger 3D printed parts together if you're trying to make a larger one out of a few smaller ones. So the first and very simplest way of doing this is with a peg and hole, but most people would generally go to a round peg and a round hole. You don't want to do this. A round hole will sag and be dimensionally off a little bit to where you don't have a good grip, and a round peg can't really be printed in a horizontal orientation to where it can be strong. You don't want the pegs to be in plane with the layers because they'll just snap off. So instead, to avoid all of these problems, take a square peg and make it diagonal. Turn it sideways, and now you have a diamond hole and a diamond peg. This diamond hole makes sure that there's no overhang areas, so it's very dimensionally precise, and you're able to print the square peg horizontally on the print bed so that it's as strong as it would ever need to be to hold the 2 parts together. But it's only held together by the actual friction of the parts themselves. Now the square peg is fine, but what if you want something that's kind of low profile? Maybe you have a really thin part or you're trying to peg around the outer edge. You don't want to do small little diamond holes, and you want something a little bit more universal and robust. Well, in this case, go ahead and do like a slab-and-slot. This is really easy to do, and you're able to create something really reliable. Just make sure that you are tapering the ends of whatever the peg is that you're putting inside of there, the slab that we're going to shove inside of there. Taper it off, round it off so that it slides in and then gets tighter as it goes in because it can connect with the walls of the part even better. And this is how you can create a really low profile connecting option. Now these are both fine, but pegs have an issue. Pegs can have a really big gap in between because as you're pressing a part together, if you have a really broad face, it can flex because it's plastic. And if it flexes and you press the 2 things together and on the outer edges they come together, but then the flex pops them back loose a little bit. So you end up with a bigger gap that you can't really overcome without making the part just stiffer so it can't flex as much, but that increases cost. You don't want to do that. So you need something that is able to press together easily, but then hold and retain in a precise position and even stronger than what you would normally have. There's a couple of options for this one. The first one we're going to look at is basically just a little S bracket. You design in a hole into the part to where you can slide in the side bracket and then slide it into a slot to where it will snap into a small slot inside of the part. This is a really good way of doing it. It is symmetric, so you can replicate that hole all throughout your part, and you can change the size of the connector piece in order to increase the amount of compression on there. This is a really good way of combining 2 pieces, and it's a very simple piece. Of course, make sure you round it all out so that it has nice, easy corners and is easy to print, but you can make this as thick as you want to make it stronger, but this is a very simple way to have a very precise joining position. Another way of doing this that's a little bit more complex and a little bit less reliable is to use basically snap fits, where you design a double-sided C-clamp to where you can press it into a slot and then it slots into a couple of holes inside of the part. This is a really good way of doing it. It's very easy, it's very intuitive, it doesn't require a lot of training like the S one kind of does. But it can be less robust because it has to be able to flex. The S is a piece of hardware being shoved into a piece of hardware. This is a mechanism, and as a mechanism, it might need to be designed just right so that it can squeeze and have enough pressure, and the latches have to contact just right. It can be tougher because you're pressing things together again rather than squeezing them together to where you can kind of do an over-center clamp thing. So of all of these options, the peg is the easiest. If you're going to use some glue, just go ahead and use a peg. Use the slab if you are going around a thin profile of a small part. You can use the S if you want it as strong as possible and still very concise and tight. And you can use the snap fit if you want something really fast and easy that doesn't require any pressure and still has a pretty tight and reliable fit. You know, sometimes you want multiple parts to stick together, but you want to do it in a way to make sure they stay together consistently, reliably, and continuously. So in this video, we're going to go through joining features, how a lot of people design them, and some better ways of actually getting them made to have your parts stick together really well. So the first and most common type of joining feature is really just a tongue and a slot. And this is a decent way of doing it because it's easy. You make a square on one side and a square on another side, and then you have them slide together or press together. And this isn't a bad deal, but it's kind of not very useful because they don't hold together very well. But if you are designing these, make sure that you chamfer the insert just a little bit. That way it's able to wedge into the main slot. And then the 3D printed layer lines can actually cause them to lock together pretty reliably. But again, you don't have any sort of pull or forcing to make sure that there's no gap in between the two pieces. Also, it's just kind of cumbersome because there's a lot of tolerance issues within it. So this isn't the greatest type of locking feature, though it's the one that a lot of people go to. But let's move into one that's a little bit more robust. Another option that a lot of people use are T-slots, and T-slots are actually pretty decent because they actually have some lateral support, so I can't pull these apart. And they're actually not too bad to design, and you can actually use the same kind of chamfering on the top of the tongue itself so that it angles up and locks into there. And this is fine, but the problem is that you now have several different tolerances to have to deal with. You also have a pretty complex first layer where this can warp and curl up when it's going down on the first layer if you're using a high warp material or want something that's robust in manufacturing. So even though it is functionally okay, it's not great. And again, you have the tolerance issues of having to keep that seam pulled together. And based on material shrinkage and other types of issues, this won't always work very well. So having something that is tight and flush, just like this, isn't always a very viable option. But there's an upgrade to the T-slot, and that is this. You can actually take the T-slot and curve it just a bit so that now you have taken the two outer flanges of the T-slot, and instead of them being straight to where they press into a hole with a friction fit, they are instead acting like springs. So that now you have a part that is able to go into the slot and lock in so that now there is no jiggle, no tolerance issues at all, and you're able to have kind of flexible tolerances that you can deal with material shrinkage and other types of issues. The other thing that we've done is, since we don't want this complex first layer on the part, we went ahead and angled the slot. And you can apply this to any of these, but by applying that angle, you now have a very simple square first layer that with some rounded filleted outer edges so that you have good corners. And then the rest of the complexity happens later in the print to where it's very easy to control and you don't have to worry about warpage on the bed or adhering to the bed. You just have it print. So you make sure that it's chamfered there, and then the two outer flanges are chamfered as well. And now you have something that can lock together super tightly, super reliably, has no jiggle, and has a very nice tight seam that will always be a very nice tight seam. The one downside of this is that you have basically this hole in the bottom of your part, which isn't always necessarily desirable, but you would also have the hole in your bottom of the part with any other types of slots, just have it outlined. So long as this is a non-customer facing feature, it can work pretty well. But there's some other types of slots that we can use. One of the more common ones is the I-slot, where you use a circular flange for the tongue. Now, the benefit of this is that it is easier to design than the T-slot because you're not doing all the XY tolerancing that is necessary. You just have one single circle that is dead centered dimensionally to the other circle. And then, of course, you chamfer this so that the two of them can lock together. And again, you get that advantage of 3D printed layer lines basically binding together so that it doesn't really want to come apart very easily if it's a really tight one. And you have a decent flushness. But again, the other problem with tongues in general is that you can have this spread at the top, this angling, to where the bottom slot is holding together, but the top of the part is not held together, so it kind of flexes like this. And that, again, is a problem with those kind of short, stumpy slots. You can, of course, make them deeper, but then you're dealing with a lot more friction in putting them together, because this can be a decent amount of effort to put together. But the I-slot is really useful because it's very easy to design, very easy to tolerance, and is generally a nice looking design. It is also technically a simpler first layer. So if you have a tongue that has to be printed face down to where this has to be against the bed and you can't do the angled thing that we showed on the spring T-slot, this is a way to get around that because these are nice smooth curves all the way around, so there's a low chance of warping or any sort of other issues on first layer that can come up. But you can also take the tongue and slot and change them just a little bit. You can actually use grip fins. Now, grip fins are a flexible feature that you have to design pretty carefully. They cannot be connected to the roof of it, but they are these small tabs all the way around the hole. And these small tabs allow you to take a much larger eye tongue and shove it right in there to where it locks in, and you have the flexibility of these outer features holding it in place. Now you can have it be a rigid feature like the regular eye slot, to where you just have a very low tolerance hole right there, which can be useful in certain situations because it gives you some flexibility. But it's also useful to actually make flexible joints or semi-flexible joints, to where you can use those grip fins to hold on to the eye tongue so that you get just a little bit of give inside of there. And it also pushes back and forth, and you have flexibility throughout while still holding on to the part reliably and centering it. And you can change the stiffness of these fins by making them thicker, making them longer, so that they grip that eye tongue even harder than they normally would. But all of these assume that you have to use tongues where two separate parts insert into each other like this. And while this is fine, it's not very robust. And again, you have that first layer problem. None of these really pull it in except for the flexible T-slot. So what is a design that we could actually use where we take advantage of 3D printing really at a large scale? Because all of these parts can pretty much be made with any other process except for the grip fins, which are impossible. They use an impossible geometry. What if we could take all of these, put them together, and make something that can't really be made any other way? Well, if you were to do that, you would end up with something like this. Now, these are just locking tabs, and the reason these don't really exist generally is because they are impossible to manufacture. This internal hole right here has two recesses inside of it, which cannot actually be machined or manufactured or molded with anything other than 3D printing. So what we are able to do is create those two recesses and then create two locking bumps on either side of this part so that these two little tongues, these flanges, flex just a little bit. And now you're able to take them and press them into that slot and have it lock. You can change the tolerances so they pull tighter. You can also change these bumps so that they are actual lock-in. Right now we made them bi-directional, so you put it together and pull it back apart. So if you're making a building kit, this can be really useful, but you can make these so that they lock in there permanently and pull it in super tight so that there is no flexure at all. But it's very quick and easy to assemble, and you don't have to deal with all the other tolerance issues of the other pieces or the first layer issues. In addition to this, we also print these parts just like this. So this brick actually sits on the build plate like this, and these flanges do not need any sort of support at all because we angled them on the bottom. So this part can come off fully complete. This part can come off fully complete. They have very simple first layers where we don't have to be concerned about some complexity that would cause them to fail or warp. And they lock together very quickly and easily, and they give you an advantage that has never been possible before. So if given the option, I would recommend doing these because these use just a smidgen less material, they're more reliable, they're easier to assemble and work with, they're also fairly easy to tolerance. So if given the choice between all of these locking tabs, I would use these. But hopefully that gives you some insight as to how to design locking features or joining features so that multiple parts of either terrain or an architecture model or maybe just a building kit can be put together in a way that is reliable and very manufacturable without having to worry about high cost or high rejection rates because of complexity inside of the model itself. 3D printing is able to create impossible geometries and able to produce those parts at a very large scale. But where is that actually practical? Well, today we're actually going to talk about how it makes stuff stick together way better than it normally would. So there are a lot of parts out there that have to be glued together. And when gluing together any type of a part, you have to deal with the glue itself. How much space does it take up? What are the tolerances when you squash it together? How far is it going to spread apart the parts? And then how well is it going to adhere to the surface? Do you have to prep that surface? Do you have to change it? Do you have to drill a hole for the glue to go into? Do you have to combine it with screws so that the glue acts as a sealant and the screws press it together? There's a lot of factors that go into that, which require a lot of extra design and a lot of extra effort on the production of the part. But 3D printing is able to integrate a whole bunch of features into the part. And one of these is actually like the part surface itself. If you are using a 3D printed part and you're going to glue a couple of them together, what you can do is actually design surface features that allow the glue to stick to the part even better. Now, of course, just roughing it up is really good. A lot of people will use sandpaper on traditional parts to do that, but 3D printing can go a step further. Since we can make parts with relief cuts, parts in designs that couldn't ever be manufactured before, you're actually able to make a hole that gets wider as it goes in, and you're able to make hundreds of them and make them really small. So now when the glue is spread across across the surface, it goes into those internal cavities and is effectively able to grab onto the part mechanically rather than just through adhesion. You get a way stronger bond because you have the part itself embedded with the glue rather than simply having the glue on the surface. These relief cuts also allow the glue somewhere to go, so the actual tolerances of the part mechanically designed are what they are rather than having the glue spread the parts apart by building up on a flat surface. So this is a way more reliable way to do it. But if you're actually running a production system, you might not want just a large surface that glue is smeared across. You might want to actually control and direct where the glue goes. And again, since you have so much control of the design, you can do patterns like this so that you denote where the glue belongs. And people just put glue there, glue there, glue there, glue there. And now you're able to basically put some direction into the design of the part itself, so in production fewer errors can happen. Because with this, there might not be enough glue down here in this corner because people are just smearing it across and there's no clear indicator if it's been placed. Whereas with this, there's a very clear patch where it belongs and how much you need in order to cover that, so it directs people implicitly in the part itself. Now, of course, that's the more interesting way of doing it, but there's really traditional things that you can do with glue slots as well when designing for 3D printing. You can just put a relief cut inside of there, and sure, you could pattern this up, rough it up, give it some ribs, all kinds of nifty geometries to make it more durable. But just having a bead to run like hot glue down or something along those lines is really useful because you can embed it straight into the part. It doesn't add any sort of post-processing. But where this gets interesting, these types of channels get interesting, is if the part is already assembled and you want to insert glue. In that case, you're able to basically create an internal channel. So we could basically create this inside of another part to where we want to deliver glue to particular areas after an assembly is made. And then once you press this together, you're able to shoot glue down from the top and it fills that entire channel. That way you don't have to prep the channel or worry about orientation as you're turning it upside down and that kind of thing. You can stick it to the surface so that it's ready and clamped down, and then you can shoot glue in from the side and it fills the entire cavity, and machining this type of a part isn't an issue. Now, of course, the slot can be made, but if you wanted to do something more interesting, like having these slots go down into a threaded insert and then fill up the threads with whatever Loctite you might be using, that could be more interesting and much more necessary if you have to deliver glue through a series of channels. So when both these blocks are printed horizontally, how do we make it so that the pin and the hole fit perfectly every single time? In this video, we're going to go through 9 different designs that you have not seen before about how to have a horizontal pin and hole fit just right. So what is the reason for wanting to print holes horizontally along with their pins? Well, the pins themselves, if you're printing them horizontally, they're in the plane of the layer lines. So this pin is much stronger than if you were printing vertically. And that's a fine and dandy deal. The same thing goes with the holes. You sometimes just have to put holes into the side of the part. Now, the issue with these types of pins is that you can end up with these types of problems where you have to have support underneath them in order to have them be crisp. And one of the worst things that you can ever do is just design a cylindrical pin straight out the side with a standard circular hole right there. None of these actually work. If you've ever printed them, you will find out that the holes end up kind of sagging or being oblong because the vertical edges sag just a little bit, creating a bad hole. So let's just start with very basic good design practices. Number 1, you don't want a simple cube with a simple cylinder standing out the side. You want to go through and optimize it a little bit. You want to chamfer the bottom, round the quarters, but now you want to go and focus on the pin and the hole themselves. The pin itself, go ahead and give a chamfer to the tip of. The reason you want to use a chamfer rather than a fillet is that a chamfer is a consistent overhang of 45 degrees as opposed to a fillet, which goes from infinite overhang to nothing. And then you equally want to fillet to the inserts to the holes so that they can slide together reliably and have a really nice fit right there. But you still have the tolerance problem of the holes, which will be always a little bit out of shape. So the very first thing that you want to do in order to get rid of that sag at the top of the holes, which is sometimes done by the slicer, sometimes done by the material, sometimes done by the print resolution that you're using. In order to have a good precision of the holes, one of the simplest things that you can do is just give the holes a small corner up on top. And you can make this fairly shallow, but this allows the hole to hold its shape without causing a tolerance issue. This way the hole doesn't compress as it's printed. And of course, you want to make sure that you have support underneath the pin itself in order to keep it crisp and not have some nasty little sagging issue. So there we go, we're done. Pins and holes, you just round out all the edges and they slide together just really easily. But not really, you're still dealing with a tolerance problem. Different materials, different print settings, different infill types, different shrinkage, different slicer, different machine will all cause these holes and pins to fit together differently. So how do you create a design that works on any material, any machine, any slicer at any time without having to worry about the clearances and tolerances varying too much so that your design breaks? So let's go ahead and go into some more advanced techniques other than just a pin and hole. Remember how I showed you this design before, which has to have the support underneath? This support ended up just being wasted material that is flicked away. Why don't you use that as actually part of the design? This way you improve the rigidity of the part and are able to use it more. This is what you end up with. You take the pin and you apply a chamfer to the bottom and top of it so that it can be printed in any orientation and you don't have to worry about support generation holding the pin in the correct shape. And of course you have to mirror it over here on the other side so it's a nice keyhole. This allows you also to use those flanges as effectively tension areas, where you have the sidewalls, which are much higher tolerance, sliding together to hold it together without having to worry about the tops and bottoms of this pin interfacing with the hole itself. It's much more reliable, you get to use material rather than throwing it away as support, and you have a much stronger side feature. But this is also sort of a waste. Why do you need a circular pin there at all if you have already chamfered it? Just go ahead and lean into it and turn it into an actual slot. With basically the slotted design, you're able to have the side compression of the hole be the only thing that is interfacing with the actual tab here. And this is better than holes because you can really tune in the fit and get along with it really well. But this is still just a standard rectangular extrusion, which is then chamfered so that you don't have overhang and a rectangular hole. This doesn't really necessarily fit always because if we change to a different material, the fit would be different. So how can you create something robust? Well, the easiest way to do that is to make something thicker. If you make that slot and make them all thicker, then what you're able to do is take this tab right here and chamfer it just slightly so that the top is narrower than the entryway to the hole and the bottom is wider than the entryway of the hole, so that as you insert, it gets tighter and tighter so that you get a really good fit that comes together really well. And then if you have a couple of them slightly offset, you can make sure that you don't have this sort of offsetting issue to where it actually self-centers. So there's plenty of ways of dealing with that. But this allows you to get a really good fit rather than a potentially loose or potentially too tight type of a fit if you're relying purely on the precision of the material that you're using, which will always vary based on print settings, materials, machines, all of that stuff. So you want to make your design as robust as possible so that it produces the part that you're looking for every time. But this is still inconsistent. You're still reliant on the tolerances of the machines and materials that you're dealing with. How do you make sure that this works all the time? Rather than simply having a solid slot right here, which has set dimensions, you can instead have two tabs which allow you to always fit into the slot exactly as intended with a little bit of pressure on the outer walls. And since they can flex quite a great deal, regardless of what machine you make it on, they will always work. But now the issue with this is that these are flat, smooth tabs, so it can slide out really easily. You don't get a really tight pressure fit or something that can mechanically hold on really tightly. This is fine for like a finding feature, but if you want to hold it together, it doesn't hold it together very tight. But that can be fixed with just the addition of a couple of small bumps and a couple of small holes inside of the slot itself. This way, when you press them together, they can actually interlock, and now you get a nice little popping in order to hold them together. Now, this is a basic demonstration of how it works, but using these grip fins with little locking features at the end and mating features on the inside allows you to get a nice, perfect, tight fit every time that holds together really, really well, and you do not have to worry about the tolerances of the material or how much shrink there is or what print settings are being used, so you can make sure that your pins always fit right into the holes perfectly every single time. Hopefully these designs were useful to you. This is the type of thing that we go through in order to educate people how to design parts that are really manufacturable. And you want this when using external services or wanting to mass produce a 3D printed part. You want it to be as robust as possible so that you don't have to tune the design to a particular machine or process. This is especially true in places like our Teleport Print on Demand app, where you can plug the Slant 3D print farm that has hundreds of machines directly into your Etsy store or your eBay store or your Amazon store, and you want your product to be made the same way. The easiest way to do that is to design the product to be manufacturable in multiple different processes at multiple different times. Many people get caught in the trap of designing specifically for their one machine, maybe it's their brand, their material, whatever it happens to be, and having their own particular bespoke settings. But that gets you stuck in an artisan kind of a layout, whereas if you do very simple design tweaks, you can have your part be made by anyone. This is also particularly useful if you are selling the files to other people who want to 3D print them as well, because as soon as you sell the file and somebody prints it on a machine that isn't good, it can also create issues with the perception of your file. How do you make something like this fit into something like this every single time without having to worry about print settings and make sure that that thing doesn't snap off every time you try to force them together? So vertical pins are something that comes up a lot. People like to make these types of pins in order to act as finding features with something that will be pressing down on top of it. But vertical pins and vertical holes can have a few tricks to them. The biggest one is just the fact that that wants to snap off every single time it gets tweaked a little bit, and the two of them don't always want to fit together. So let's start off with very basics right here. This part is very poorly designed. The reason is because that top cylinder is just a cylinder, there is no filleting anywhere, and that hole is the exact same size as the bottom. So let's go ahead and get past this basic kind of noob mistake and move on to a correct one. First of all, the bottom hole has a fillet in the top so that it's possible for something to be pressed into it, to be funneled into it. That's the very simple one right there. This hole is also made just a hair larger than the actual pin that is meant to go into it, so that there's margin there around the shrinkage of it all. This is about 1/4 of a millimeter. You can sometimes go up to 1/2 millimeter depending on the shrink of your materials, but 1/4 is generally fine. The pin itself is where we're gonna focus. Now, with that original red one, it was just a cylinder straight up in the air, but it's small and thin. The very first thing to make a 3D printed part stronger is to make it fatter. You increase the diameter of that pin, and now it won't break off quite as easily. But then, where is it going to break off? Well, it's gonna break off down at the base of the pin. So fillet that just a little bit, and it will match perfectly with the fillet on your hole. And then, in order to make sure that it can actually enter into the hole reliably, we're gonna round off the top of it so that, again, the two want to join together, as opposed to just a sharp hole and just a sharp pin trying to find each other and press together. You don't wanna do that. So this is basic good design. You add in a little bit of clearance in there for the actual parts to fit together, you round off all the edges, and you allow them to actually insert correctly by deburring and getting rid of sharp corners and that kind of thing. These are all good general rules. And of course we follow all those rules with all the rest of the cube as well, putting a chamfer on the bottom, rounding the outer corners, all the things you're supposed to do. But that's the basic stuff. We want to make this even stronger yet. So maybe this is under a lot of torque or it's sliding or something like that, and you want to make sure that there's no way that can snap off. Well, the other really basic sort of solution is to just make it shorter. These are generally better for like sliding features and that kind of thing, but they can still be useful. There is no reason to make it any longer than it has to be. If you can make it shorter, and that decreases the amount of torsion that it can occur on the base of it all. Okay, that's it for all the easy things to do. But why does this want to snap off? Well, if a force is applied to the top right here, this is effectively a lever arm, and it's going to try to bend across this lower corner down here, and then it's going to split along the layer lines. So you engineer around that. Since the layers need to have a large amount of contact between themselves in order to not split very readily, what you can do is, rather than simply just having the outer skin of a circular cross section, you can actually increase the amount of area that the layers are touching. And the very simplest version of that is doing this. Use a cross pattern. It still has the same function. It presses right into it just like that, but you have more strength because these individual sections are able to give you more strength in the direction that the push is happening. As opposed to this that just has that outer skin, and then as soon as a crack forms, it breaks on through. This has a lot more direct structural stuff in that axis to hold it together. Now we're gonna get into some subtle design tricks on this, because while this fits into this, you're gonna have to tune your clearance and your tolerances in order for those to fit every time. And if you ever move to a different machine or a different material or a different printer settings or a different resolution, it's all gonna break down. So how do you make sure that this actually fits into there every single time? The very first solution is a very simple little chamfer here. You can see just a slight draft angle. So you can make the base slightly wider than the hole, and you can make the top narrower than the hole, so that as you're pressing in, the top definitely goes in, and then you can force it in the rest of the way. So that chamfer allows you to get it worked in there, and then this cross-section design allows it to kind of wear in. So if you're gonna repeatedly do this, you can actually make sure that it starts to fit the other hole well, rather than simply going in and getting locked. This is a really good benefit of this, is that there's not direct binding of the outer walls together, and you don't have to worry about that clearance. This is a much more universal way of getting it done. But you can evolve this even more. Again, you want to sharpen off the tip of it all so that it's able to insert into the hole reliably and make sure that the base is filleted out. Or you can apply the chamfer to have it just fit in there just right and move from there. Both of them have the main cross section so that you have the maximum amount of strength that you can have, because there's the most interlayer adhesion, most surface area of each layer that you can get a hold of, which is so much better than just a simple round pin. But if surface area and outer surface contact is the goal, why not just maximize it? Why not just go the whole way? These still can have infill and are still wasting surface that could be used. Those inner corners right there could be filled up with material if you had the circle. But the problem with the circle is that it can be filled up with infill. So with our final design here, what we have done is we have wrinkled the outer edge of the circle so that you have the maximum amount of material on the outer edge where the crack would want to form, so that there's as much resistance to that as possible. But in addition to that, I put a cross on the inside of there so that this upper pin is effectively fully solid. This is something called micro features. And with micro features, what you do is you basically put a 0.2 millimeter slot into your model. And what will happen is that that effectively turns into walls inside of your model. So you're able to apply solid areas to particular areas of the model. And with those slots, I can actually drive them down, not just to the surface, but deep into this part a little ways, so that you get the maximum amount of strength that you can possibly get from a 3D printed part here. Because while all the rest of it is printed with regular infill, the pin is effectively solid, and it has enough outer surface area that cracks cannot form on those outer edges. And with a little bit of chamfering and rounding the top and all the other basic design rules, it will press together and fit perfectly every single time, regardless of what color, what material, or anything else you want to use. Now, why is it so important to make sure that you design CAD like this so that it's reliable, independent of your print settings? Well, if you ever wanted to mass produce this or have it produced on demand as a product through a print farm, like in our teleport service, where you can just upload a file and send it off to somebody, you want to make sure that it can be printed right off of any type of machine at any given time, without needing tuned or tweaked. If you're tweaking slicer settings, you are not designing a product. You are being an artisan. It's like carving wood. But if you actually design it well, then it's something that can go into a factory and be produced reliably every single time. Will create a really good quality product for your customers and be more reliable than anything else you could ever possibly do. So hopefully these tricks have been a little bit useful to you in turning something like this into something like this that can actually be strong and reliable, rather than just a bunch of pins getting knocked off in shipping. You have something that can be structural, reliable, and really, really good fitting. Have a great day, everybody.